Pickup students is going to be Unit 9, Day 17. Today we are talking about half-angle identities. So far we know the sum and difference identities, we know the double angles, the quotients, the reciprocals, the Pythagoreans. We've got a lot of identities under our belts, and there is just one more type to learn, and it happens to be the half-angle identities. To prove to you what the half-angle identities are all about, we're going to use this identity right here for cosine of the double angle. This is one that I hope you're pretty familiar with. Cosine of 2x, one of the three options would be 2 cos squared x minus 1. And you can see what I have off to the side here. It says solve for cosine x. So to get cosine x alone, I'm going to add the 1 to this side. So that's going to give me that 2 cos squared is equal to, if I add the 1 over 1 plus cosine of 2x. And then I'm going to divide both sides by 2, continuing to get cosine alone. I get 1 plus cosine of 2x divided by 2. And then last step here, of course, to get rid of the squared, we're going to take the square root of both sides to get that cosine of x is equal to, and when I take the square root of both sides, I of course need plus or minus out in front, square root of 1 plus cosine of 2x and divided by 2. Now, this may not look like much of a half-angle identity yet until I do a quick let statement. So I'm going to say, let's let x equal the angle theta divided by 2. So what that's going to do is it's going to create over here where I have x, I'm going to replace that with theta over 2. So you can now kind of see cosine of half of theta would equal the following. Plus or minus the square root of 1 plus cos of, if x is theta divided by 2, multiplying that by 2 just gives you cosine of theta on the inside there. So now this is the half-angle identity for cosine. Cosine of half of an angle would equal plus or minus the square root of 1 plus cos theta over 2. Now that plus or minus out front, it's not both. It's going to be one or the other. And we're going to have to decide which one it is. And I'll talk about how we're going to do that in a second. But similarly, we have formulas for sine of a half angle and tan of a half angle. So similarly, if I had sine of theta over 2, that would equal plus or minus the square root of. If I had done the same thing except use 1 minus 2 sine squared, use that identity instead, that's going to leave you with 1 minus cosine theta over 2. So there's the identity for sine of half of an angle. And then finally for tan of the half angle, that's going to equal plus or minus the square root of. Is going to be 1 minus cos theta over 1 plus cosine theta. Okay, and that kind of makes sense because if you do sine divided by cos, you'll have the 1 minus cos on top, the 1 plus cos on the bottom. The divided by 2 parts will cancel out. So these are the 3 last new identities that we have to know. So to go back to that question from before, though, how do you decide with the plus or minus? Well, it turns out it has something to do with quadrants. So if theta is in quadrant 1, okay, if this angle right here is in quadrant 1, we know that that means that theta is somewhere from 0 to 90. So what that means is that if I cut everything in half, because I'm looking for theta over 2, that would mean that theta over 2 is somewhere from 0 to 45 degrees. So again, just literally dividing everything by 2, we would get that theta over 2 is from 0 to 45, which is still actually in quadrant 1. So if you have a quadrant 1 angle to start, cut everything in half, you're still in quadrant 1. All right, let's kind of extend this out. What if theta is in quadrant 2? Well, quadrant 2 is from 90 to 180. So if I cut everything in half, we're going to get 45 on this end is less than theta over 2, which is less than 90. Half of a quadrant 2 angle is definitely in quadrant 1. And I'm sure you can generate the other 2 cases here, but let's keep going. So we got theta in quadrant 3. That's going to be 180 to 270, which would make theta over 2 somewhere between 90 and half of 270, which is 135. That's quadrant 2. And then finally, last but not least, if theta is an angle in quadrant 4 from 270 to 360, we're going to have that half of all of that. Oops, you guys can't see this maybe. Let me move this down. Half of that would be from 135. Half of 360 is 180. So somewhere from 135 to 180 is also in quadrant 2. So what you can see is that half of the angle brings us either into quadrant 1 or quadrant 2. And that's going to make a pretty big deal if it's a tangent or cosine equation. We know that tan and cos in quadrant 2, since you're my all-star trig class, that in quadrant 2 only sine is positive, cos and tan would be negative. So it is all sort of dependent on where the original angle theta is and then how we can use that information to figure out something about half of the angle. All right, let's get to some practice with half angle identities. So a question might look something of the form: if tan theta equals 24/7 with theta in quadrant 3, find cosine of theta over 2. Okay. So cosine of theta over 2 is going to equal plus or minus the square root of 1 plus cos theta divided by 2. That's just copying the identity from earlier. And in order to figure out cosine of theta, that's going to be the substitution here, we're going to have to use the information about tan theta. Okay, we know we're in quadrant 3. We know that tan is opposite over adjacent, so that would be opposite of 24, adjacent of 7. Now, because we're in quadrant 3, that's why tan is positive, but it's really because it's a negative divided by a negative. It's tough to remember to put those negative signs there, but it is important. If I do a quick Pythagorean theorem, we're going to get the hypotenuse to be 25. That might be a pattern you're familiar with already. But once I have that filled in, I can now go ahead and start making some substitutions here. Now, let's also talk about that plus or minus while we're here. We said if theta is an angle in quadrant 2, that theta divided by 2 is in quadrant 2. I don't know if I said that correctly earlier a minute ago, but if theta is in quadrant 3, we've already determined that if I take the bounds of quadrant 3 and I cut them in half, that has to be something in quadrant 2. So if I'm dealing with cosine in quadrant 2, I know that this is a negative result because only sine is positive there. So we're going to put a big negative in front of the radical. 1 plus cosine theta. Cos theta would be adjacent over hypotenuse. That's negative 7/25 divided by 2. And then it's really all about the algebra of cleaning this up. It's pretty easy substitution if we know the identity. This is going to be a complex fraction whose LCD is 25. So you're going to multiply the top by 25 and multiply the bottom by 25. So that's going to be the negative square root of, distribute the 25 across the top, you get 25 minus 7. On the bottom, you get 50. All right, continue simplifying. 25 minus 7 is 18 over 50. And although at this point you could take the square root of the top and the square root of the bottom to simplify, I would encourage you to simplify that fraction if possible. It's going to make your life so much easier. Watch what happens. Divide by 2 on the top bottom, you get 9/25 when you reduce. And of course, the square root of 9 is 3. The square root of 5 on the bottom is, or 25 on the bottom is 5. So negative 3/5 is the exact value for cosine of half of this angle. So given tan of this original angle in quadrant 3, cosine of half of that angle has the exact value of negative 3/5. Okay, so kind of cool that we can use identities even if we want to double an angle, but here's an example of where we're cutting an angle in half and finding its exact value. All right, here's another example. Let's find the exact value of sine of 15 degrees. So we've done this before. We've done this in the case of taking two angles that add or subtract to this amount. And probably the easiest way to do it is 45 minus 30. So sine of the difference of two angles, of course, would be sine, cosine, cosine, sine, where here's one angle and there's the other angle. And just to kind of shortcut that, because we've done this method before, we get radical 6 minus radical 2 over 4. Radical 6 minus radical 2 over 4. But could we have also approached the same example from the perspective of a half angle identity? So in other words, what angle divided by 2 up here would equal 15 degrees? Well, that's going to be really easy to determine, because if I double this to get 30, well, then when I cut it in half again, that would get me back to 15 degrees. Why is this going to make sense as an alternative way to do sine 15? Because 30, of course, is a special angle. So if this is my value of theta, For sine, it's plus or minus the square root of 1 minus cosine theta divided by 2, which would be plus or minus the square root of 1 minus cosine of 30 degrees over 2. Now, as far as the plus or minus go, we already know that it has to be positive. The angle is 15 degrees. So 15 degrees is definitely quadrant 1, which means we're definitely looking at a positive quantity here. So it's going to be the positive square root of 1 minus whatever cosine 30 is. Well, cos 30, if you want to draw a quick triangle here, that would be 1 radical 3 and 2. So cos 30 would be adjacent over hypotenuse. That's radical 3 over 2. And then all over 2. Similar to what we saw up above here a moment ago, we were going to multiply the top and bottom by the LCD, which in this one is 2. Not because the 2 down there, by the way. It's really because of this 2. So that's going to equal the square root of 2 minus radical 3. And then 2 times 2 on the bottom is 4. Now, in the end, this is going to equal the square root of 2 minus radical 3 in the numerator. There's really nothing fancy to do up there. You can't simplify the way that looks any further. But the only reason I'm separating this is that the square root of 4 in the denominator is just good old 2. And that's the final answer. That is an exact way to represent sine of 15 degrees. But wait, I thought this was an exact way to represent sine of 15 degrees. So the question is, are those two radicals in fact equal? And the best way to check that, and I'll have you do this quickly on your own, double check that those decimals are the same on your calculator. Type this in and then type that in. And if they're the same decimal, then I'm convinced that those radical forms are in fact the same. They look quite different. But if you were to try and simplify this and do some kind of crazy rationalizing tricks, you could probably make it look just like this one. Okay. All right. So we'll leave it like that for now. Let's go ahead and take a look at a little bit more practice with half angles. So for example, if I asked you to find the exact value of cosine of pi over 8. Pi over 8. All right, well, pi over 8, if we do these questions, remember that when it's in radians, I've always encouraged you to convert it to degrees real quick. So pi over 8 times 180 over pi, if you do that conversion, 180 divided by 8 winds up being 22.5 degrees. And then if you ever have half of a degree, it's a pretty good hint that you need a half angle identity. The only way to generate this number right here is by cutting an angle in half. You're not going to have two special angles that add to this, subtract to that amount. There's nothing that's going to work unless you cut a special angle in half. And what special angle am I dividing by 2? If you're not sure, just double it, right? Double this and it will tell you what angle to cut in half. Happens to be 45 over 2. So remember, this is your value of theta that you're going to plug into the identity, plus or minus the square root of 1 plus. Half angle identity for cos is a plus up here, and it would be cosine of 45 over 2. So it's a little bit tricky because students sometimes get confused and they put 45 over 2 in here, even though this is cosine of theta over 2, and here it's just cosine of theta. So whatever your theta is, just make sure you plug it in correctly. 22.5, by the way, is an angle in quadrant 1. So I can just choose the positive end of this radical, right? All the functions are positive in 1, so it's going to be square root of 1 plus. See, cos 45, if you need the 45 triangle quick, it's 1, 1 radical 2. Cosine's adjacent over hypotenuse, which is 1 over radical 2, but I like to keep that rationalized right away. So you get 1 plus radical 2 over 2 over 2. So LCD here is 2, multiply the top and bottom by 2. Square root of, distribute, 2 plus radical 2 on the top, 4 on the bottom. And then last minute here, leave the radical over the top part. But again, just like we saw in the last example on the bottom, the square root of 4 is just 2. So the exact value, lots of 2's in there, but the exact value for cos of pi over 8, which is 22.5 degrees, is the following: radical 2 plus radical 2 underneath there, divided by 2. Half a degree, it's got to be a half angle. Whereas in this last case, we had two options. To get 15, you could do 45 minus 30. You could also do 30 divided by 2. Both would work. If here we're kind of stuck with using a half angle identity for sure. All right, and the last thing that we'll do today is, just because I know you missed it, let's prove an identity with a half angle. The identity is 1 minus tan squared of half of the angle x equals 2 cosine x over 1 plus cosine x. All right. I'm going to work on the side with the half angle identity, see if I can simplify this and eventually make it look like what's on the right side there. All right, so the half angle identity for tangent is being squared, which is kind of nice because the half angle identity for tan has a big radical over it. So it's going to be 1 minus, that half angle is the plus or minus the square root of 1 minus cosine x over 1 plus cosine x. That's going to get squared. Squaring the radical, like I said, makes it go away. It doesn't even matter if it's plus or minus. Squaring it keeps it positive. So we're going to get 1 minus the fraction 1 minus cosine x over 1 plus cosine x. All right, so what we're doing is we're technically subtracting two fractions. If I write that this is 1 over 1, right now we're subtracting two fractions. And to do that, you have to make a common denominator. So we're going to multiply this fraction on the left by 1 plus cos on the top bottom so that I can eventually combine it with this fraction over here. It's going to be 1 plus cos over 1 plus cos. Maybe you'll like this better. Instead of subtracting that binomial, why don't I change this to addition here? But when I change to addition, I'm going to distribute that negative to both of these terms. So make it a negative 1 plus cosine x up here. Okay, don't change the LCD of 1 plus cos. But that's kind of an important step so that we don't make a mistake. Instead of subtracting, I like distributing the negative and changing it to addition. Notice what happens now. 1 and negative 1 go away. Cosine x plus another cosine x becomes 2 cosine x's. I like that. That would be all over the LCD of 1 plus cosine x. I like that because these are in fact the same. Got all my symbols in there. Okay. Looks a little scary at first, but after plugging in that half angle identity, just using that formula, squaring it gets rid of the radical. It's all about the algebra of making a common denominator with the fractions that we have. Okay. All right, that's it for our lesson on half angle identities. A couple more days of identities left, and then we get to move on to some more exciting stuff with trig. Have a great rest of your day.